Hello students, I am explaining the science topics for CBSE 10th, especially physics and chemistry. This will help you to get good marks. Okay. In this revision series, I am first dealing with magnetic effects of electric current. Okay, please do remember it is a revision series, little bit faster than regular classes. And in this chapter, first topic is Oersted experiment. Oersted experiment is the basic idea of relation between the current and magnetic effect, and the current also have magnetic effect. Let us see how what is the relation between current and magnetic effect. To understand the relation between current and magnetic effect, Oersted experiment is there. We have to discuss this experiment. Let us take one battery. Positive terminal connected to ammeter. Ammeter is connected to resistor. Resistor is connected to long straight conductor or copper wire. Okay, and this is a magnetic compass having needle, and the long straight wire is connected to switch. Switch is connected to negative terminal of battery, and current is flowing from positive direction to negative direction. Okay, and if the current is flowing in this circuit, there is a deflection in there is a reading in the ammeter. Once current flowing inside this circuit, and there is a reading in the ammeter. Okay, during this while current is flowing, and we have to bring one compass bring near to the straight copper wire, and the needle in the compass shows deflection. If you switch off the current, if you switch on the current is flowing, reading in the ammeter, and current is start flowing inside the circuit, and there is a deflection in the magnetic compass, and needle short shows showing deflection. When you switch off the circuit, and there is no zero reading inside the ammeter, and there is no deflection in the compass. So when the circuit is when the current is when switch is on and current is flowing, and there is a deflection in the magnetic compass. When you switch off, there is no current in the there is zero reading in the ammeter, there is no deflection in the compass. So based on this observation, the relation between current and magnetic effect, and current also have magnetic effect. When there is a deflection in the compass, when there is no current, there is no deflection in the compass. Based on this observation, there is a relation between electricity and magnetism. There is a this concept is the foundation for. Next, we are drawing magnetic field lines with the help of a compass needle. Let us take this is a bar magnet, south pole and north pole. If you place it compass here. Okay, this is the compass. Okay, compass have north pole and a south pole. If it is south pole, it attracts north pole. So if it is north pole, opposite is south pole. And again, bring this compass to next position. Okay, it occupies north and it is south. And if you do it, the deflection is shows this pattern. Here, if it is north pole, this is the south pole, and this is north pole. North pole attracts south pole. This is the pattern of this deflection shows pattern of magnetic field. By using bar magnet and a compass, we can draw the pattern of magnetic field lines. Next, we define north pole. The end point of compass needle move north towards north is called north seeking pole or north pole. Next to south pole. And every magnet have, we know that if you break any number of parts, and every part of the magnet have two poles. The end of compass needle pointed towards south is called south pole or south pole. So every magnet have two poles. Now we have to understand the magnetic field. Magnetic field have both magnitude and direction. We have seen the compass needle showing the deflection in previous example. If you move from north pole to south pole, and we find the one pattern. If you move if the compass needle is moving closer to the poles, the deflection is more. The deflection is near the pole. Deflection is more. Deflection is more. In previous example, we seen there is a compass deflection and we draw some pattern, and deflection is more at poles and less at away from the poles. Hence, based on this observation, magnetic field have both magnitude and direction. And now we can find the direction of pattern of magnetic field. Okay, suppose let us take let's draw a pattern of magnetic field lines. North pole and the south pole, and the direction of magnetic field outside the magnet is north pole to south pole. We need to draw very carefully. North pole to south pole. This is the direction. Here at north pole, the magnetic field direction is outward, away. Here towards south. Okay, towards south pole. The magnetic field direction is from north pole to south pole outside by convention, and there is a magnetic field inside and uniform and the same at all points inside the magnet. From the direction is south pole to north pole outside, north pole to south pole inside, south to north. Okay, this is the pattern of magnetic field lines, and they form closed loops. They never intersect each other. By convention, magnetic field north to south outside, north pole to south pole, and vice versa, south pole to north pole inside. So based on this observation, suppose if you take this line, it will away Outside the magnet, the field direction is north pole to south pole, and inside south pole to north pole. They form closed loops, and they form, based on this observation, they form magnetic field lines are closed loops. Okay, and two magnetic field lines, they never intersect. Second property. This is the first property, and the second property, they never intersect. The magnetic compass will not show two directions. If the magnetic compass do not show two directions at same point, we can say they never intersect. Okay, magnetic field lines have two properties. First, they form closed loops outside from north pole to south pole, inside south pole to north pole. Hence they form closed loop, and the two magnetic field lines are, they never intersect. These are the two important properties of magnetic field lines. And one more observation: if the lines are closer and the magnetic field is more, if the distance between the lines is more, the magnetic field is weak. And one more time I am explaining, if the distance between the lines is small, the magnetic field is more. If the distance between the magnetic lines is more, and the magnetic field strength is weak. Now we have to find the magnetic field in a current carrying conductor. We have to find the direction of magnetic field when a current is passing through straight conductor. Let us see this direction, and indirectly we have to find the relation between magnetic field direction with respect to current. Suppose the current, see this circuit, positive terminal, current is flowing from positive terminal to negative terminal. Here it is magnetic compass, and it is a copper wire. When current is flowing from north to south, the deflection is towards east. When you change the if current is flowing from north to south, the deflection is clockwise. When you change the direction of current, you have to reverse the terminals. So minus and plus. In this case, current is in first case, current is flowing from north to south. In second case, the current is flowing from positive terminal to negative terminal, because we change the direction of current. So current is flowing from south to north, the deflection is west. From this observation, we can say when the current is flowing from north to south, the deflection of compass is clockwise or towards east. The magnetic field is east towards east. When the current is flowing from south to north, the deflection is towards west. When the direction is towards left, the magnetic field direction is towards west. Current is north to south, the magnetic field is towards east. When the current is flowing from south to north, the magnetic deflection is towards west or anti-clockwise. Now we have to discuss magnetic field due to current through straight conductor. Okay, when current is passes, this is the copper wire, it is a straight conductor. When it is connected to battery, through ammeter and variable resistor and switch, the path is closed and current starts flowing from positive terminal to negative terminal. The direction of current in the copper wire is north to south. So we have to find the direction of magnetic field. How we find the direction of magnetic field? By using the north pole of the compass. The north pole of the compass. Suppose current is flowing from south to north. The north pole deflect towards east. When next time we have to reverse the terminals, and the direction of current moving from south to north. The deflection of the compass is towards west. Okay, if you from this observation we can say, if you change the direction of current, the deflection in the needle also reverses. So magnetic field direction also changes. So if you change the direction of current, the direction of magnetic field also changes. This is the first important observation. Second point, suppose let us take copper wire. If you pour iron filings around this copper wire, and you will observe the pattern of concentric circles. You observe the pattern of concentric circles. Okay, when you increase the current in the copper wire, the concentric circles are very closer. When the current, the magnetic field is more. Okay, when you decrease the current in this copper wire, the concentric circles are bigger, the magnetic field is uh, less or weak. Okay, this is the second observation. And the third observation is, when you are moving away from this copper wire, the concentric circles are becoming, the magnetic field decreases. When you are coming closer to the copper wire, the concentric circles are small and very closer, the magnetic field is more. From this observation, there are three observations in this experiment. First, if you change the direction of the current, and the magnetic field direction changes. Second, if you increase the current, the concentric circles are closer, the magnetic field is more. If you decrease the current, the concentric circles are bigger and the magnetic field is weak. And the third observation is, if you move away from the copper wire, the concentric circles are bigger, the magnetic field decreases. And this concept, the magnetic field in a straight conductor, explained by right hand thumb rule. When the current is flowing upward, thumb represents the direction of current and fingers represent the direction of magnetic field. When the current is flowing upward, the direction of magnetic field is anti-clockwise. When the current is flowing downward, when the current is flowing downward and the fingers are anti-clockwise, the magnetic field is anti-clockwise. The thumb represents current and fingers represent magnetic field. When it is upward, when the current is upward, the magnetic field is anti-clockwise. When the current is downward, the magnetic field is clockwise. Right hand thumb rule explains the direction of magnetic field in a current carrying straight conductor. Right hand thumb rule. This is right hand, this is a thumb, these are fingers. Okay, it gives the relation between current in a straight conductor and direction of magnetic field. Let us take, this is the right hand, represents current, and fingers represents magnetic field. When the current is moving upward, the direction of magnetic field is anti-clockwise. When the direction of current is downward, the direction of magnetic field is clockwise. Suppose if current is upward, the direction of magnetic field is anti-clockwise. When the direction of current is downward, the direction of magnetic field is clockwise direction. Now, in previous case we discussed magnetic field is due to current in a straight conductor. Here we are finding magnetic field in a current passing through circular loop. We have to find when current is passes from positive terminal. This is the circular copper wire or circular copper coil. Okay, we have to find when current is passing from positive terminal to negative terminal. Okay, so we have when current passes, we have to find the direction of the magnetic field in a circular coil. Here in previous case we discussed about right hand rule. When current passes through a straight conductor and find the magnetic field direction. Now we are finding magnetic field direction in a circular loop. Now current is flowing from positive terminal to negative terminal. It forms concentric circles. Okay, it forms concentric circles here downward and upward. Okay, when the magnetic field depends upon the inverse square distance. If you are moving away from this coil, the concentric circles are bigger and bigger. Okay, the magnetic field becomes weaker. And here also, if you are moving away from away from the copper coil, the concentric circles become bigger and bigger. If you reach the center of this coil, the magnetic field line become straight, and the direction of magnetic field is from here clockwise. So it represents south pole, it represents north pole. Okay, magnetic field here in this picture is created from north pole to south pole. Okay, straight lines are formed at the center of the coil and its concentric circles are formed at extreme ends of this coil. This is the behavior of magnetic field in a circular loop. And next point is, if you are increasing the number of turns of this coil, number of turns of the coil, the magnetic field becomes n times. The magnetic field becomes n times, it multiplies. Okay, if you increase the number of turns of circular coil, and the magnetic field also increases. So if you want to understand the behavior of the current in a circular loop, we have to apply right hand rule for a circular loop. This is called Maxwell-Cox-Screw rule. See, like right hand thumb rule. This is very important. Next, we discuss magnetic field due to current in a solenoid. Solenoid means a copper wire insulated in the form of cylinder. We call it as solenoid. Solenoid. Now, in this case, we have to observe the pattern of magnetic field in bar magnet is same as solenoid. Let's see how the pattern of a magnetic field of bar magnet is same as the pattern of magnetic field of solenoid. Let's take copper wire. This is a copper wire connected to battery. This is a negative terminal, this is a positive terminal, and a switch, and one end of this coil is connected here. So current is flowing from positive terminal to negative terminal. Okay, and we are already observed when the current is passes through circular loop and we have concentric circles. Direction here, and one more concentric circle. Here in the extreme hand we have concentric circles. Here straight lines. This is the north pole and this is the south pole. The direction here. This is a knot, and when the current is passes through this circular coil, which is wrapped in the form of cylindrical circle, it forms concentric circles at extreme end, at extreme north end, at extreme south end, and at the center of this coil, we know that, and concentric circles are formed at north end and south end, and at the center the magnetic field lines becomes very straight of circle. When current is passes through circular coil, the magnetic field lines are straight at the center of this coil, and those concentric circles at extreme ends of this coil. The magnetic field direction here at the center is south to north and outward is north to south. Here outward north to south, inward south to north, outward north to south, inward south to north. So bar magnet also have same pattern, inside south to north, outside north to south. Based on this observation, we can say the pattern of magnetic field of solenoid is same as pattern of magnetic field of bar magnet. So we can treat solenoid as a bar magnet, and it is also called as electromagnet. It is temporary in nature. When you switch off the when you switch off the circuit and current stops flowing and magnetic field loses its nature. Okay. Next topic, magnetic field due to current in solenoid. First we have to understand the definition of solenoid. Take insulated copper wire wrapped in the form of cylindrical shape. Suppose this is a copper wire wrapped in the form of cylindrical shape. This is called solenoid. Let's draw the shape of solenoid. And next thing is we have to compare the pattern of magnetic field in the solenoid is same as bar magnet. Whether is it true or not? Let's see. This is a copper wire wrapped in the shape of solenoid, which is connected to battery. Minus this terminal switch. Now let us understand. Already we discussed the magnetic field in a circular coil. In a circular coil, we form concentric circles at the extreme ends and the straight lines at the center of the circular coil. Here, one more in this direction. Here also extreme end. This is also one more concentric circle. They do not intersect, and these are the straight lines at the center of the south. The magnetic field direction is north to south here, and inside towards south, away from south. So here, when the current is passes through circular loop, there is two types of patterns: concentric circles at the extreme ends of the circular coil, and here concentric circles, and straight lines at the center of the coil. Okay, same bar magnet also have same pattern. At the center of the bar magnet is the magnetic field is uniform, which is direction from south to north. Outside there is a circular loop from north to south, so they form closed loops. Here also closed loops, and straight lines inside the bar magnet. Here also straight lines inside the solenoid. So we can say the pattern of magnetic field of solenoid is same as the magnetic field of bar magnet, and so it is we are also called as electromagnet. Solenoid as a electromagnet. It is same as similar as bar magnet. Next, electromagnet. This is a temporary magnet. We are using a strong magnetic field of solenoid to magnetize a magnetic material like soft iron. We call it as, this is a soft iron. We are magnetizing by using magnetic field of solenoid. We call it as electromagnet. Hello friends. Today I am explaining about force in a current conductor magnetic field. See, we have to discuss the relation among force, current and a magnetic field through this observation. Let us take a aluminum rod AB connected to wire which is connected to key and battery. Another end of AB is connected to negative terminal of battery, and place a magnetic field. Let us take current is passing through the rod AB in the presence of horseshoe magnet, and upper part south pole, down part north pole. And we have to observe the behavior of the aluminum rod in the presence of horseshoe magnet, and also current passes through it. Now current is flowing from positive terminal to negative terminal through the aluminum rod B to A in the presence of horseshoe magnet. Let's find the observation. And we have to find the behavior of rod, and which is having current and in the presence of horseshoe magnet. Let us take this is a horseshoe magnet, and the chalk piece is the aluminum rod B end and A end, and current passes from one terminal of battery to another terminal of battery, and its we need to observe the behavior of aluminum rod in the presence of horseshoe magnet. Suppose current flowing, the AB turn left, and if you in the presence of magnetic field. So first observation is the aluminum rod is turning left in the presence of horseshoe magnet. Now we from this observation we can say uh, next observation, we need to change the direction of current, and now the chalk piece, now the aluminum rod turn right side. Okay, let's see how it now it is turning right side. If you change the direction of the current, and the deflection of the aluminum rod AB also changes in the presence of horseshoe magnet. Now from this observation we can say there is a relation between the direction of current and the motion of the displacement of the aluminum rod AB. So the motion of aluminum rod depends upon the direction of current. This is the first observation. Now we have to find the deflection of aluminum rod in the presence of horseshoe magnet. Suppose south pole is upward, north pole is downward, it is deflecting left side. Now if you change the direction of the south pole and north pole, move the north pole upward and south pole downward, the deflection also changes. So from the second observation we can say aluminum rod, the displacement of aluminum rod depends on the magnetic field. First observation, there is a relation between displacement of rod and the direction of current, and the second observation, displacement of rod and the magnetic field. And deflection happens when the field, the current, and these three are mutually perpendicular. This the relation among force, current, and the field explains by left hand rule. Thumb represents motion of the rod, and first finger represents magnetic field, direction of magnetic field, and second finger represents current. When they are mutually perpendicular, there is a displacement of the aluminum rod. Fleming's left hand rule explains the relation among force, current, and magnetic field. Based on this observation, there is a relation among force, current, and magnetic field explained by Fleming left hand rule. Okay, this is very useful. Hello, next chapter, Human Eye Colorful World. Let's discuss important things in this chapter. First, we will understand the structure of human eye and what are its main parts of human eye, its functions of each part. This is a very important. First, we are seeing the structure of our human eye. Human eye is like a camera. Okay, so first part we see the light enters through our outer layer is called cornea. Cornea is the protective layer. When light falls on our human eye, it enters through cornea. Behind the cornea, there is ciliary muscles. Ciliary muscles adjust the focal lengths. If object at different distances, it gets clear, adjust the focal length so that we can have clear image on the retina. So retina acts as a screen. First cornea, ciliary muscles. Next iris. Iris, this part. Behind cornea there is a iris. Iris which controls the size of the pupil. This is the iris which controls the size of the pupil. So iris controls the size of the pupil. Pupil is regulates, next part, pupil is regulates the amount of light entering into the eye. Suppose suppose if light is more light is falling on our eye, light automatically closes because it sensitizes pupil. Okay, first next part is eye lens. Eye lens acts a main part. Next part is retina. Retina have a lot of light sensitive cells. When light falls on the lens, it forms image on the retina. Retina acts as a screen. First part, cornea. Cornea is a protective layer. It is the outer part of the our human eye. Next, second part is ciliary muscles. Ciliary muscles adjust the focal length so that we form when object at different distances we get clear images. And third part is iris. Iris which controls the size of the pupil. Pupil regulates the amount of light entering into the our human eye. And last, retina acts as a screen. So our human eye forms inverted and real image. And next, optic nerves, this is the optic nerves generates signals and sends signals to the brain. So these are the very important parts of the our human eye. Next topic, power of accommodation. Already we discussed the structure of our human eye. Our human eye made up of fibrous and jelly material. So our human eye have ciliary muscles is one of the main part. The main role is adjust the focal length. If focal length is adjusted, we will able to see the objects clearly when objects are at different distances. Suppose we can able to see the long mountains, or we can able to see distant birds. Okay, because of adjust of focal length. So adjust of focal without if adjusted focal length is not adjusted, we will not able to see the objects at different distances. Okay, so ciliary muscles adjust the focal length so that we will be able to see the images clearly. Now ciliary muscles are sometimes relaxed, sometimes stressed. When ciliary muscles are relaxed, the lens become thin, focal length is increases. So we will able to see the distant objects clearly. Okay, suppose ciliary muscles are stressed. When you are bringing object very close to eye, it is stressed or cataract. So lens become thicker, focal length decreases. If focal length is decreases, we will able to see the near objects clearly. So here focal length is increasing or decreasing when lens are thin or thicker. When it is lens becoming thinner and thicker, so when ciliary muscles are stressed or relaxed. So focal length is increasing, decreasing. This is very important. It is indirectly connected to ciliary muscles. When ciliary muscles are relaxed, focal length increases. We can able to see the far objects. When ciliary muscles are stressed, we will able to focal length decreases. We will able to see the near objects. So focal length is increasing and decreasing. The adjustment of focal length, like increasing, decreasing focal length, we call it as power of accommodation. Suppose a normal person, we will able to see the object. If you put objects very close to eye, he will not able to see. At minimum distance, he will able to see. The minimum distance of a person is 25 centimeters. This minimum distance, beyond that minimum distance, he cannot able to see the objects. That minimum distance is called near point or least distance of distinct vision. The normal human person, the minimum distance is 25 centimeter. It is also called as near point. For the capacity of person at which he able to see long distances is far point. The far point of normal person is infinity. It varies from person to person. Generally, for old people, the crystalline lens are cloudy and milky. This is called cataract. So these defects are curated by only surgery. So if there is a problem on the adjustment of focal length, there are three eye defects: myopia, hypermetropia, and presbyopia. Okay, we'll discuss one by one in next topic. Due to adjustment of ciliary muscles, and there is a difficulty in adjustment of ciliary muscles. So there are three eye defects. First is myopia, second hypermetropia, third presbyopia. Already we discussed myopia, hypermetropia. Presbyopia means the person who have presbyopia, he suffers with both myopia and hypermetropia. Generally, old people suffer with these kind of diseases. Okay, when presbyopia, ciliary muscles becomes very weak. So to correct presbyopia, we are using bifocal lens. Bifocal lens means concave lens, convex lens. We are using both concave and convex. Concave lens at upper part of the lens and concave lens lower part. Okay, with upper part the person will able to see distant objects. With convex lens, the person able to see near objects. So in today's, to correct this kind of presbyopia problem, we are using lenses or surgical surgeries. So this is the solution. So with this topic, we have completed the function structure of human eye, functions of each part, and the power of accommodation, defects of human eye. Okay, these are very useful and scoring subject. Hello students, there are three eye defects: myopia, hypermetropia, and presbyopia. First, we will discuss myopia. Myopia means near sightedness. He can able to see near objects but cannot see distant objects. Okay. First, we will understand the what is myopia through diagram. Suppose this is our human eye. Okay. So, suppose if object is placed at distance O in front of eye, the light rays coming from O falls on the retina. You can able to see the objects clearly. Now in second situation, if you move this object little far, we already said myopia, we can see near objects, cannot see far objects. If you move the object from point O to beyond O dash, so the light rays coming from far object O dash falls in front of the retina. So this causes myopia. Okay, to correct myopia, we are using concave lens. If you place concave lens in front of eye, the light rays coming from O dash converge on the retina, the eye defect is corrected. Generally, this eye defect arises because of two reasons. First, excessive curvature of eye lens. Second, elongation of eyeball. Okay, to correct myopia, we are using concave lens. Okay. Second defect, hypermetropia. Hypermetropia is also called as far-sightedness. In this case, the person who is suffering with hypermetropia can see distant object clearly but cannot see near objects. Let's understand the hypermetropia through diagram. Suppose if you are placing object at point N, okay, the light rays coming from N falls on the retina. We can able to see the objects clearly. And if you, I already said, in a hypermetropia, we cannot see a distant object, cannot see near objects. Okay. Now if you move the object from N to N dash, the light rays coming from N dash is falls behind the retina. If light rays are coming from N dash fall behind the retina, causes the eye defect hypermetropia. We cannot see the near object clearly. To correct this hypermetropia, we are using convex lens. If you use convex lens, the light rays coming from N dash falls on the retina. We can see the objects very clearly. Here N is called near point of hypermetropic eye. N dash is called near point of normal eye. Generally, the person who do not have hypermetropia, the near point is 25 centimeter. In case of hypermetropia, the near point is more than 25 centimeters. Okay. Generally, hypermetropia arises because of two things. First, focal length is too long, and second, eyeball become too small. Okay. These are two important things which are frequently asking in the exam. Next topic, power of accommodation. This is very important idea. First, we discuss the structure of human eye. Human eye have eye lens. Eye lens is a fibrous and jelly materials, and it have ciliary muscles. The already we discussed the role of ciliary muscles is adjust the focal length. When ciliary muscles are relaxed, the lens become thin and the focal length f increases. So when focal length increases, our human eye will able to see distant objects clearly. Okay, for normal person, he can the distance at which he can see is very infinite. Okay. Next, when ciliary muscles are stressed, suppose you are bringing the object very closer to human eye, it is stressed and are contracted. The ciliary muscles are when you bring the book very close to our human eye, it is because stressed. So the ciliary muscles are contract. When ciliary muscles are contracted, and the lens become thicker. When lens become thicker, focal length is decreases. You can able to see near objects clearly. So in this entire scenario, the ciliary muscles are increasing the focal length, decreasing the focal length. Suppose if you are very bringing any object very close to the human eye is straining. Without strain, at a minimum distance at which we can able to see the object, we call it as power of accommodation or near point or least distance of distinct vision. For normal human person, it is 25 centimeter. If you are bringing an object at 25 distance without strain, this is a minimum distance at which we will able to see the objects very clearly. If it is minimum at if you are bringing any object less than 25, you cannot, your eye will strain and your ciliary muscles are stressed, you will not able to see the objects clearly. The minimum distance at which we will able to see the object is called power of accommodation or near point or least distance of distinct vision. So here the power of accommodation is increasing and decreasing the focal length. Decreasing the focal length through ciliary muscles is called power of accommodation. Next, we discuss refraction of light through prism. Let us take prism A, B, C with equilateral triangle. Each angle is equal, and angle A is called angle of prism. And let us take, when you are sending light from A to glass and glass to A, when there is a difference in medium, we know that there is a refraction. Now light is entering from A to glass and it gets refracted, and again light coming out from glass to air, and again it is refracted. The ray, let us take incident ray PQ and emergent ray BC and refracted ray BC and emergent ray DE, and PQ is incident ray, BC is refracted ray, and DE is emergent ray. Let us draw normal here. So this is a normal, and draw another line, second normal too. Okay, normal line, the angle between incident ray and normal ray is called angle of incidence, and angle between the refracted ray and normal ray R1, here R2. Now and now draw, this is point C and angle between normal to and emergent ray is called angle of emergence. This is the incident ray, this is refracted ray, this is DE is emergent ray. Let us take I is the angle of incidence. So here R1 is angle of refraction. So already we discussed angle A is called angle of prism. So next angle E is called angle of emergence. And now we have to find angle of deviation. If you extend incident ray and this emergent ray and this angle between incident ray and emergent ray is called angle of deviation. Angle D is called angle of deviation. Angle of deviation is related to extension of first incident ray and extension of backward extension of emergent ray. The angle between incident ray and emergent ray is called angle of deviation, and here this angle is called angle of prism. So in refraction of light through prism, we have to mainly observe angle of refraction, angle of deviation. Next topic is dispersion of white light by glass prism. When you send it's a prism, when you send white light, it is refracted from different paths and it is splits into, when you send white light through prism, it splits into various paths. It travels through, splits and travels through different paths, and each path is unique. It forms VGR, a band of colors is called spectrum. So it forms different colors based on the angles. We are classify the colors, and this white light is splitting into 7 colors. And if it's band more, is a band of colors and band of colors. This white light is splitting when it passes through prism. This splitting of white light is into 7 colors is called dispersion of light. Each path is unique and it makes different angles, and the violet makes more angle. Violet bends more. This is called red, and bends less. Red bends less, and violet color bends more. There are VGR 7 colors. This 7 colors is called band spectrum of colors. The splitting of white light when it passes through prism is called dispersion of light. When it bends more, it forms with violet color. When it bends least, it forms red color. And rainbow also is one of the example for dispersion of light. When water droplet acts as a prism. Suppose sun rays. Sun rays are coming from here, and it is splitting. White light is splitting, and there is a first refraction, then splitting of white light, and splitting of white light is called dispersion, and again coming back and forming 7 colors. This is formation of rainbow. Formation of rainbow is also example for dispersion of light. This is a water droplet. Formation of rainbow. Sun. Once again, when sun rays are falling on the water droplet, there is a refraction because different in medium, and white light passes through water droplet. Water droplet acts as a prism, and it is splitting the light. Splitting light is called dispersion of light, and coming back, internal reflection. This is the formation of rainbow. First refraction, then dispersion, again internal reflection. This process is called, this is the process of formation of rainbow. Formation is rainbow is also example for dispersion of light.